Okay, in this video we're going to be looking at more on sequences, and so specifically we're going to be looking at monotonic sequences. We say a sequence A sub n is said to be monotonic increasing if for all n in the natural numbers, A sub n is less than or equal to A sub n plus 1. So the next term is larger than the previous one. A sequence A sub n is said to be monotonic decreasing if for all n in the natural numbers, A sub n is greater than or equal to A sub n plus 1. So the succeeding term of the sequence is smaller than the preceding term. Bounded sequences. A sequence A sub n is said to be bounded from above if there exists a number m, so a real number n, such that A sub n, for all n, A sub n is less than or equal to m. A sequence A sub n is said to be bounded from below if there exists a number n such that for all n, A sub n is greater than or equal to n. A sequence A sub n is said to be bounded if it is bounded from above and below. In other words, there exists a positive number m such that for all n, the absolute value of A sub n is less than or equal to m. Okay, and so very similar to bounded functions. For example, the sine of x is bounded above by 1 and bounded from below by negative 1. Okay. All right, so let's do some examples. So number 12 and 13 down there, it says determine whether each sequence is monotonic and bounded. All right, so number 12, A sub n is equal to 1 plus 1 over n. And we want to see if it's monotonic increasing or decreasing. So we're going to look at a couple of terms of the sequence to kind of get an idea what it's doing. So A sub 1 is equal to 1 plus 1 over 1, which is 2. A sub 2 is 1 plus 1 half, which is 1 and 1 half. A sub 3 is 1 plus 1 third, which is 1 and 1 third. So it appears that maybe it's decreasing. It looks like it's getting smaller. So if it's getting smaller, then A sub n would be greater than or equal to A sub n plus 1. So we don't know that yet, but we're going to see if we can figure that out. Now by definition, A sub n is 1 plus 1 over n, and A sub n plus 1 is 1 over 1. A sub n plus 1 is going to be 1 plus 1 over n plus 1. That's just by definition. So we could subtract 1 from both sides of the inequality. So 1 over n greater than or equal to 1 over n plus 1. We can cross multiply and the inequality will be preserved. We're not multiplying by any negatives. So n plus 1 is greater than or equal to n. That's certainly true if you really want to keep going. 1 is greater than or equal to 0, so we do have a true statement, and then we could reverse our argument, and we would have, in fact, shown that A sub n is greater than or equal to A sub n plus 1, and so this is a decreasing sequence. Now, if we want to show that it's bounded, we got to just figure out a number that all the other terms are equal to or smaller, or just smaller, really. So we're going to see, is it bounded? Well, so it's certainly bounded above. Is it bounded below is what we're going to determine. So we're going to suppose is bounded below by 1. So would A sub n always be greater than or equal to 1? So let's find out. That'd be 1 over n. Just that's the definition. Is that greater than or equal to 1? Well, we can subtract 1 from both sides. 1 over n is greater than or equal to 0. That's certainly true. So yes, so this is monotonic decreasing and bounded from below. And we'll get a theorem in a little bit which will tell us that it's going to converge. Now, we already know that we could compare this to the function f of x is equal to 1 plus 1 over x. And as x goes to infinity, that function is going to go to 1 plus 0, or just 1. So we know that this sequence is going to do what that function does. So again, on the previous video, we compared it to functions where the sequence agrees with the functions at all the positive integers. Okay. All right, so let's look at that number 13. So number 13, we have A sub n is equal to 1 minus 1 over n, and we're going to see what's happening. So 1 minus 1 over 1 is 0. A sub 2 is 1 minus 1 half, which is 1 half. A sub 3 is 1 minus 1 third, which is 2 thirds. So it appears that maybe it's increasing. So is a sub n less than or equal to a sub n plus 1? We're going to find out. So by definition, a sub n is 1 minus 1 over n, and a sub n plus 1 is 1 minus 1 over n plus 1. So again, we can subtract 1 from both sides. So as negative 1 over n is that less than or equal to negative 1 over n plus 1. Go ahead and multiply it by n and n plus 1. So you have negative n minus 1 less than or equal to negative n. So I didn't multiply by a negative, so I don't need to reverse the inequality. Okay, then we can add n to both sides, and we have negative 1 is less than 0. So that's certainly true, and so certainly a sub n is less than or equal to a sub n plus 1. And so that tells us that this sequence is in fact increasing. So we have this increasing sequence. And so we know it's bounded from below by 0, so is it bounded above also? So is it bounded above? Let's find out. Well, maybe it's bounded above by possibly 1, because we got 0 and then 1 half and then 2 thirds. The next one would be 3 fourths and then 5 6, etc. So is a sub n bounded from above by 1? Let's see if this is true. So is 1 minus 1 over n, is that less than or equal to 1? Negative 1 over n, that's a negative number, less than 0. That's a true statement. So yes, this is bounded from above. So this is a bounded sequence from above. And we'll have a theorem in a minute here which will state that if you are monotonic increasing and bounded from above, then you're going to converge. We can also get this limit by comparing this to the function f of x equals 1 minus 1 over x. And if we take the limit of that function as x goes to infinity, the 1 over x is going to go to 0, so the limit of that function will be 1 minus 0. And so the sequence will do the same thing. 1 minus 0 is 1. Okay. All right, so let's go look at that theorem. So before we get to the theorem, we have something called the Completeness Axiom. And it says every non-empty set of real numbers has a least upper bound. Oh, I'm sorry, I missed it because I have my pause and buttons in the way. Okay, so every non-empty set of real numbers that has an upper bound has a least upper bound. Sometimes it's abbreviated LUB, or sometimes it's called the supremum. Every non-empty set of real numbers that has a lower bound has a greatest lower bound, sometimes abbreviated GLB, and it's also called an infimum. So we have a theorem here. Monotonic bounded sequences converge. We'll do the case where we have monotonic increasing and bounded from above. So for our proof, we're going to suppose that a sub n is a monotonic increasing sequence that is bounded from above. A sub n is a set of real numbers bounded from above, so by the completeness axiom it has a supremum or a least upper bound. Okay, let k be a real number, and that's going to be the supremum of a sub n. So for all n in the natural numbers, a sub n is going to be less than or equal to k, which is your supremum. Okay, so that is your least upper bound. Okay, let epsilon greater than 0 be given. Since k minus epsilon, so I have k plus epsilon and k minus epsilon there, since k minus epsilon is not an upper bound, k is the least upper bound or the smallest upper bound. So since k minus 3 is not an upper bound, there exists an n in the natural numbers such that a sub n is greater than k minus 1. So here we can look at our sequence. So here's a1, a2, a3, a4, all the way up to a sub n is going to be finally larger than k minus epsilon, because k minus epsilon is not an upper bound. That means somebody in the sequence has to be larger. Since a sub n is monotonic increasing, for all n greater than this big N, a sub n is greater than or equal to a sub big N, which is greater than k minus epsilon. So, for all n greater than n, k minus epsilon is less than a sub n, which is less than or equal to k. And so that means a sub n minus k, that's the distance between a sub n and k, is within epsilon. and thus a sub n is going to converge to its supremum, or in other words, the limit as n goes to infinity of a sub n is equal to k. Okay. All right, so let's go ahead and do an example here. So we're going to show that a sub n, which is equal to 5 plus 2 over 3 to the n power, is monotonic and bounded, and then we're going to find its limit. So first thing we're going to do is we're going to look at some terms, and this kind of gets us an idea, okay, is monotonic increasing or decreasing? All right, so a sub 1 is 5 plus 2/3. So 5 and 2/3. A sub 2 is 5 plus 2 over 3 squared, so 5 and 2/9. A sub 3 is equal to 5 plus 2 over 3 to the third, so 5. Sorry, that's supposed to be a 3 here. It looks like it's a 2. Okay. All right, so that'd be 5 and 2/27. And it looks like the fraction is getting smaller attached to the 5, so this would be a decreasing sequence. Now, to really show that it's a decreasing sequence, we can go ahead and look at seeing if we can manipulate the inequality a sub n is greater than or equal to a sub n plus 1. So if we can show that's true, then we'll have shown that this is a decreasing sequence. So a sub n less than or equal to a sub n plus 1, so question mark. Well, a sub n is 5 plus 2 over 3 to the n by definition. A sub n plus 1 is going to be 5 plus 2 over 3 to the n plus 1 by definition. We'll subtract 5 from both sides. So 2 over 3 to the n is greater than or equal to, and so 2 over 3 to the n, that's the same thing as 2 over 3 to the n times 1/3. That might be enough to convince you, but we can certainly divide by 2 over 3 to the n on both sides. That's a positive number, so we don't need to flip the inequality. So we have 1 is greater than or equal to 1/3, and that's certainly true. And so we have verified that this is a decreasing sequence. Now we want to show that it is bounded from below. So what might it be bounded below by? So we're going to suppose that a sub n is greater than or equal to 5 for all n, which means it's bounded from below. So 5 plus 2 over 3 sub n, that's what a sub n is. We want to know, is that greater than or equal to 5? Well, we can subtract 5 from both sides. And 2 over 3 to the n, is that greater than or equal to 0? That's certainly true. If you want to keep going, we could clear the fraction. Is 2 greater than or equal to 0? That's certainly true. And so we have verified that this is bounded from below. And so if it's decreasing and bounded from below, it's bounded from below, not above. Then a sub n is converging. Okay, so the limit as n goes to infinity of 5 plus 2 over 3 to the n is going to be 5 plus 0, or just 5. Okay, we could also compare it to the function. Well, we'll just look at the 2 over 3 to the n. So the function 2 over 3 to the x is the same thing as 2 times 1/3 to the x power, and that's a exponential model, or an exponential function, where the base is less than 1. And so if the base is less than 1, then the function is going to go to 0 as x goes to infinity. Okay, and so the 2 over 3 to the n is going to do the same thing as that function. It's going to go to 0, and so this limit is going to converge to 5, which, so 5 would be the infimum of this sequence. Okay. All right, so I think we'll have 1 or 2 more videos. This is a rather long section. There's a lot of review concepts and some new concepts to introduce. We'll see you next time.